So, just a reminder, worksheets 16 through 18 are due on the 16th. Homework number 2 is due on the 16th, and exam number 2 will be on the 16th. That'll be on chapters 16 through 18. It'll also be about 60 questions, similar to the previous exam. Your grades for the first exam are up. They may look a bit odd because they're curved, but I included a curve for it. So you can see where you're at. I'm working on getting through grading all the other stuff. Sign in if you haven't signed in. So we were talking about, we finished off last time talking about the states of matter for water and how it takes a lot of energy to go from one phase of matter to another. So evaporating water consumes a lot of energy, so cools things, and condensing water releases a lot of energy, so warms things up. Humidity is a measure of the amount of water vapor in the air. So there is air in this room and it has a certain amount of water vapor in it. And water vapor, the air can hold a certain amount of water. It has a sort of maximum that it can hold. And this depends on the temperature primarily. The hotter it is, the more water it can hold. But if you talk about the humidity, you can talk about the humidity in a couple different ways. You can talk about like precisely how much water vapor is in the air. The amount of water vapor in the air varies quite a bit. If the air is filled to capacity, if it has all the water vapor it can contain, it's considered saturated. And that capacity is temperature dependent. Warm air holds more water than cold air, which is part of why you get so dry in the winter. And also why when you breathe out in the winter, your breath turns foggy, because the air in your body can hold a lot more water vapor than the air out in a cold day. And when you breathe out, you release very humid air, and it has more water vapor in it than can be in the cold air. And so as it cools down, that water condenses out to form fog. Vapor pressure is a measure of the portion of the pressure of the air that comes from water vapor. And vapor pressure depends on temperature. It depends on several factors, but how much water there is and things like that. But the pressure that you can achieve from like above liquid water depends on temperature. So if we're going to measure humidity, there's a couple of ways you can do it. One, you can talk about how much water vapor is in a unit of air. So how many grams of water per kilogram of air. So if you have a kilogram of air, it has so many grams of water in it. It turns out, though, that doesn't match what we feel very well. It turns out the actual more commonly used value that relates more to what humans experience is the relative humidity. Relative humidity is the ratio of the air's actual vapor content. So how much water vapor is in the air compared to its potential maximum? How much could it be in the air? So how much water vapor would be required to saturate the air? So if you have 3 grams per kilogram of water vapor in the air and it could hold 6, you'd be at 50% relative humidity. But you could change how much water vapor the air can hold by changing the temperature. So you could cool it down and then it could hold less. Or you could warm it up and then it could hold more. So when you cool a packet of air down and don't change the amount of water in it, its relative humidity goes up. And when you heat a package of air up, its relative humidity goes down. So this is affected by changing either moisture or temperature. But relative humidity is a lot closer to what we feel, because it's the relative humidity that affects things like how well we can sweat. Because, when you sweat, stuff isn't going to evaporate very well if there's no room in the air for more water. So when humidity is 100%, sweating doesn't work very well. Now, so for example, at a constant temperature, the relative humidity will increase as you add water vapor to the air. So you have 1 kilogram of dry air with 5 grams of water vapor at 25 degrees Celsius. This has a relative humidity of 25%. Because the saturation mixing ratio at 25 degrees Celsius, the maximum you can fit in the air is 20 grams per kilogram. Here, if some of this water evaporates and you get 10 grams of water vapor in the air, then you're at a humidity of 50% because you're halfway full. And then here, if you get up to 20, because you evaporated even more water vapor, you're at 100% relative humidity. And that's the limit to what you can hold, so that's where it will stop. But you can also affect relative humidity with temperature. If you have 1 kilogram of dry air with 10 grams of water vapor in it, it has at 25 degrees Celsius, it has a saturation mixing ratio of 20 grams per kilogram. So that has a relative humidity of 50%. If you cool it down to 15 degrees Celsius, well, the maximum water vapor it can hold is now only 10 grams per kilogram. So its relative humidity has increased up to 100%. And lastly, if you cool it down even further, down to 5 degrees Celsius, then it will only hold about 5 grams of water vapor. And what will happen is the extra 5 grams will fall out as liquid, will condense as liquid, and the relative humidity will remain at 100%, because you can't get more than 100% humidity. When you get more than 100% humidity, what happens is some of that water vapor turns into a liquid and condenses out. So as the temperature varies through the day, your humidity would vary. If you have something that tracks humidity and temperature, you'll see this happen. Like, you cool a room down by turning on the AC or something, you'll see the humidity go up. So throughout a day, as the temperature goes down, the relative humidity goes up. And as the temperature goes up, the relative humidity goes down. Now, so if you change the temperature of a room, you can change the relative humidity. Now, sometimes things like an air conditioner will actually also act as a dehumidifier and take some of the water vapor out of the air completely, but that's a different. So here's an example of variation in humidity with temperature. So again, the higher the temp, if the amount of water vapor in the air stays the same, when the temperature goes up, the relative humidity goes down. And when the temperature goes down, the relative humidity goes up. This is why it's, if you don't want water to evaporate, like you're watering your lawn or something, best to do it at a cool portion of the day, like early in the morning. Now, another way we can talk about how much water is in the air is we can talk about how much we need to cool the air down for water to start to condense out, for it to hit saturation. That temperature is the dew point temperature. So if you had 10 grams of water per kilogram, the dew point temperature would be at 15 degrees Celsius. If you started at 25 degrees Celsius, and 50% humidity, and you cool down to 15, then you'd hit dew point. And the dew point is useful because it tells you the temperature below which you'd start to get condensation. So if you have like a packet of air rising up through the atmosphere, getting colder, when it hits the dew point temperature, it'll start to form clouds. So for example, if the temperature drops below the dew point, you get dew, fog, or cloud formation. If it's at the ground, like on a surface, that's dew. If it's touching the ground, a cloud at the surface, that's a fog. If it's high in the air, it's a cloud. Now, water vapor requires something on which to condense. On a surface, it usually just condenses, you get dew on your windows or on grass blades or your car or whatever. Out in the atmosphere, it uses various aerosol particles or various little particles in the air to condense around, to form droplets or ice crystals. So here's a map showing dew point temperature on a typical September day. You can see over on the East Coast, where it's humid, the dew point temperature is a lot higher. And then in the desert here, the dew point temperature is very low because it's very dry. There's very little water vapor in the air. So this is, how dew point varies across the country on a typical September day. And dew point is actually a measure of just how much water is in the air. So here is a short video about dew point.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what the dew point temperature is and why it results in the formation of dew. A household example of dew can be seen in this image. Here's a nice cold glass of iced tea that has condensation all over the outside. So what's happening here is little water molecules that are in the air surrounding this glass are perfectly stable out there in the air. They're happy to be in the vapor phase unless their temperature gets lowered. And when they up against this glass, they encounter much cooler temperatures. And that causes them basically to give up some heat and exit the vapor phase and condense. So they become part of the liquid phase and they coalesce in these little droplets on the exterior of the glass. You may have seen the same thing in your yard on a cold morning. When you walk outside, you'll notice that there are dewdrops on the grass or perhaps covering your windshield of your car. What's going on here? Well, it basically has to do with how saturated with water the air is. So here's an experiment. We've got a flask, and in this flask are 7 grams of water vapor. That's our sort of starting point. And this is at 20 degrees Celsius. And what we're going to do is, over the course of the experiment, we're going to cool it down, going towards the right. Once we get it down to 10 degrees Celsius, you can see that the air has become saturated. Okay, so basically its relative humidity is 100%. In the first example, basically we've got 7 grams of water vapor content, but the saturation mixing ratio, which you can get from table 12.1 in your textbook, that was 14 grams. So 7 divided by 14 was 50%. So that air was only 50% saturated relative to water. But by the time we get it down to 10 degrees Celsius, we have a new mixing ratio, and that's 7 grams. So 7 divided by 7 gives you 100%. So that's the relative humidity there. If it gets any cooler than that, some of that water vapor is going to have to condense out of the air. And that, of course, is what we want to do next. So now we're going to drop it down to 0 degrees Celsius. And at 0 degrees, the saturation mixing ratio is 3.5 grams. And so what's going to end up happening here is that that's all the water vapor that air can hold. And so it's going to remain at 3.5 grams, which is 100%. But 3.5 grams of water vapor in the air when you had 7 to start off with means that 7 is going to have to leave the vapor phase and enter the liquid phase. It's going to condense, and so you end up getting 3.5 grams of water at the bottom of the flask. This is a map which shows dew point temperature. So basically, this map considers how saturated the air is, how much water is already actually in the air. And so, therefore, how much would you have to cool that package of air in order to get it to condense? And you can see in more humid areas of the country that you don't have to cool the air nearly as much in order to get it to condense out of the air. So here in the southeast, for instance, you've got dew point temperatures that are around 70 degrees. That's really, really different from, say, Nevada and Utah. Over here in the American Southwest, you can see the dew point temperature there is all the way down at 20 degrees. So you basically have to drop that temperature of that air a lot further, an additional 50 degrees, in order to trigger condensation from that air. So why is that? Why is the dew point temperature so much lower in Utah than it is, say, in Tennessee? Hopefully you deduce that it's all about humidity. Utah has relatively arid air, and so you've got to cool it a lot more before you can get its water vapor to condense out. In general, Tennessee has much more humid air, and so basically you don't have to cool it nearly as much because it's already so much closer to saturation. Thanks a lot for your attention. This has been another Smart Figure.
So there's a few ways to measure humidity. The traditional method uses what's called a psychrometer, which has two thermometers, one of which is just a regular thermometer, and the other one is a wet bulb thermometer. It's got a piece of cloth around it that's kept wet. And the temperature will be the same at 100% humidity, but if the humidity is lower, evaporation will cool the wet bulb thermometer more, and there'll be a difference in temperature. And the greater the difference between the thermometer readings, the lower the relative humidity. This is the old-fashioned way to do it. The modern way it's done, and in any humidity device that you get pretty much these days, we'll use, well, most. But there's a few other ways to do it. If you have any sort of electronic humidity reader that has that is electronic, he uses capacitance. It turns out if you measure the capacitance of the air, so you could basically just set up a couple of plates with air in between and see how the capacitance varies. That varies directly with humidity. So you can just measure the capacitance of the air and get the humidity off of that, which is a lot more convenient than using a psychrometer. There are, I think, some mechanical humidity measuring devices that use like things that bend with the humidity, but so if you have like a dial humidity reader, I think that's might work that way. I don't know so well on those, but I do know about the electric ones. And this is a psychrometer. This is a sling one psychrometer, which is the portable version, where you dip the wet end in room temperature water and then you whip it around so that that water will evaporate and you'll get a clear difference in temperature. There are also designs where they have that wet bulb covering is like one end is in a little thing of water, so it wicks up water and always stays moist. Then is tables that you once you get the two temperatures, you basically look them up in a table and work out what the humidity is and the dew point and all sorts of information. So we're starting by talking about adiabatic temperature changes. Adiabatic temperature changes occur when you have a package of air that moves and is compressed or expanded due to a change in the air pressure, generally as it moves up or down. But no heat energy is added or subtracted. Adiabatic transitions are ones where nothing goes in, no heat goes in or out. You can have a change in temperature because you might change volume or change something otherwise, but no heat is going in or out. Temperature and pressure and volume are changing, but no heater is going in or out. So adiabatic for air, for a packet of air, this is what's happening when you have like a lump of air that's just rising up because it would say slightly warmer than its surroundings. So the dry adiabatic rate for unsaturated air. Rising air will expand and cool at about 10 degrees Celsius per 1,000 meters. So every 1,000 meters you go up, the temperature will drop by 10 degrees Celsius. If it's descending, descending air will compress and warm up by about 10 degrees Celsius at 10 degrees Celsius per 1,000 meters. This is for unsaturated air. This is for air that is not fully saturated, not at its dew point. So once you hit the dew point, you will start condensing water vapor, and that will change the rate at which it cools, because the condensing of water vapor releases heat, and so you'll cool less as you go up. So the wet adiabatic rate, when rising air cools and condenses and forms clouds, this liberates the latent heat stored in the transition from gas to liquid. So when you go from gas to liquid, you have to release energy. And that basically reduces the rate of cooling. And so this cuts the rate of cooling for wet air down to almost, it can be as much as half the rate, so 0.5 degrees Celsius per 100 meters. This was 10 degrees Celsius per 1,000 meters, so it's 1 degree Celsius per 100 meters. So the rate will vary from 0.5 degrees Celsius to 0.9 degrees Celsius per 100 meters due to the relative humidity. How much water is in the air. But if you have condensation, that condensation releases heat and causes you to cool down at a lower rate. So your temperature will drop faster as you go up while it's until you hit the dew point, and then the rate it drops will slow down. So here, as we have a packet of air rising up. It starts at 32 degrees Celsius at the surface. At 1,000 meters, it's at 22. At 2,000, it's at 12. And then it hits, at 3,000, it hits its dew point at 2 degrees Celsius. And now its rate of cooling is only 5 degrees Celsius per 1,000 meters. So it goes, so instead of dropping another 10, where it would go to -8, what you would expect if it kept with the same pattern, it only goes to -3. And then at 5,000, it's down to -8. So that rate of change slows down. And that can lead to these situations of atmospheric stability, whether because that rate of change slows down, there can be differences in the rate at which the temperature changes, which could affect the temperature compared to the surrounding air, and basically it can end up keep going up, or it can stop going up, kind of thing. So there are several processes that cause air to rise up. One of the simplest is orthographic lifting. That is just air hits a slope, it gets pushed up the slope. Elevated terrain acts as a barrier. The air gets moved up the slope. What you get often, if you have a big mountain, you get rain on one side where the wind is hitting it, and the other side is very dry. It's called a rain shadow desert. So if generally your wind is coming from west to east, the western side of the mountain is going to be green and wet. The eastern side of the mountain is going to be dry, because all the water falls out as the air gets pushed over the mountain. Then you can have frontal lifting, where cool air acts as a barrier to warm air. So when warm air encounters cold air, it gets pushed up. Fronts are what causes, we talk about, if you watch the weather, it'll talk about fronts all the time, because fronts cause storm systems. If you have a cold front, you have cold air slamming into warm air, it rapidly raises up the warm air, creating really big clouds with lots of water in them, which cause thunderstorms. A warm front is more gradual because it's warm air pushing over existing cold air, and it causes more spread out rain. But fronts where you have cold air and warm air meet, the warm air gets pushed up, the water turns into clouds and generally falls on our head as rain. So fronts are part of the storm systems called middle latitude cyclones. So here's orthographic lifting. As the wind carries it up, on the windward side, you get very wet. And on the leeward side, you get very dry. So here, the Sierra Nevadas, the windward side is very wet. And then on the leeward side, the Great Basin is sort of a dry scrubland. And this is frontal lifting. So as cold air slams into warm air, the warm air gets pushed up over the cold air and forms big thunderheads. You get more dramatic storms with cold fronts than warm fronts because in a cold front, the cold air is moving, so the warm air gets pushed up faster than when the warm air is moving, it's more gradual. Then convergence, when air is coming together in a place, if you have air coming in from both sides, well, the only way it can go is up. So it goes up. So air flows together and then rises up. This is a low pressure zone. The geography of Florida causes a lot of convergence because it's this peninsula surrounded by ocean. And so it's warmer along the peninsula, because it's land that heats up by the sun, and cooler on either side. So the air flows in and goes up, and it rains all the time in Florida. And then you can have localized convective lifting, which is just some spot on the ground gets warmer, warms the air above it, that warm air rises. So when unequal surface heating causes packets of air to rise because of their buoyancy. And that's just much smaller scale. So here, for example, is convergence over Florida. You can see where Florida is because of all the clouds. Because the air is coming in, and once it hits the land, it basically rises up. And so you can see the outline of the land of Florida with the clouds there. So here's a video about these methods that drive air up: frontal wedging and convergence. The fronts are when two packages of air of different temperatures run into each other and the warm air gets pushed up. Convergence is when air from multiple directions converges and rises up.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how convergence results in frontal wedging and cloud formation. Let's begin by taking a look at localized convective lifting. This is what happens when, say, you've got one area of the ground like this patch of farmland here that's darker than the surrounding areas. It ends up absorbing more of the sun's energy, and as a result, it warms up the air that's immediately above it. That warm air then wants to rise because it's less dense than the surrounding cooler air. That generates this package of air that rises up, and that's called a thermal. Eagles and vultures really like to find thermals, and they coast around on them as a way of saving energy. Eventually that thermal will cross the condensation level. Basically that's the level where the temperature is low enough that the water vapor is no longer stable in the air, and it starts to condense out of the air and glom onto little dust particles and things like that, and that makes clouds. Okay, so that's the basic situation. Now consider this image. This is a satellite image looking down at the coast of Florida. So the coast of Florida basically would be outlined something like that, and you can see that there are clouds over the land but not over the sea, or not nearly as much over the sea. So what's going on here? Okay, The land, we know, tends to get warmer faster, and it tends to get to a higher temperature than the ocean does. The water has a really high heat capacity. It can absorb lots and lots of heat before its temperature changes very much. So the land is warming up, the air over the land is rising, and that generates these packages of air that are crossing that condensation level and forming clouds. Now, when that air is all rising away from the land, what does that do to the air pressure there on the land? Well, it reduces it, and that's going to cause air to move in from the surrounding ocean to take its place. So you end up getting this air pattern that is shown here by the green arrows, cold air moving sideways off the ocean over the land, getting warmed up, and then rising. And then that rising air, of course, generates the clouds. So this is the sketch in your textbook that sort of demonstrates that basic idea. This is called convergence. Now this is the part of the textbook that we really wanted to get to here. We have two air masses that are colliding. One is a warm air mass and the other one is a cold air mass. The cold air mass is moving in from the right. The warm air mass is moving in from the left. As the two meet, because the warm air is less dense than the cold air, the warm air ends up getting shoved up into the air. And of course, then it's going to cross that condensation level, and that's going to trigger the formation of clouds. And then those clouds are going to likely drop their load of moisture as rain. So this is where these massive thunderstorms frequently come from when you end up getting a cold front moving into your area, because that warm air is essentially getting shoved upwards by this wedge of cold air that shoves its way underneath. Now imagine a similar situation where we took away the cold air and instead replaced it with something like a mountain range or something like that. What sort of situation would you get there? Well, whether it's a mass of cold air or whether it's the Sierra Nevada mountains, we end up seeing basically the same thing happening. So air masses are forced up and over that obstacle, and they can cross the condensation level as they go up and over, and that ends up resulting in this case, the rain shadow effect. So all the clouds basically get pulled out by the mountains. They end up dropping their precipitation load on the mountains, and then there's very little moisture left by the time that those air masses get over towards the Great Basin Desert. Thanks very much for your attention. This has been another Smart Figure.
So this is localized convective lifting, where you have some darker area warms up more than the surrounding area. You get a thermal, and then when that packet of air reaches condensation level, it'll form a cloud. This can be very local. As mentioned, eagles, vultures use thermals to save energy, because it's basically a free height. So you basically, if you glide into a thermal, you can use the thermal to go up, and you can just keep gliding without having to expend energy to rise up. So the critical factor that affects what occurs with weather is atmospheric stability. You may have heard of something called what was it? It's a thermal inversion. That's a particular case of this as well. So stable air is one that is air that resists vertical displacement. Stable air is cooler than its surroundings and denser than its surroundings. It wants to sink, so it undergoes no adiabatic cooling. And absolute stability occurs when the environmental lapse rate is less than the wet adiabatic rate. That means the rate at which the atmosphere cools is less than the rate at which wet air cools. The slowest that air will cool, which means always as you go up with a packet of air, it's always going to lag behind the cooling of the surroundings. It's always going to cool faster than the surroundings, sorry. And that means it's going to end up being colder than its surroundings. So here is absolute stability. This is what it looks like. So if you have some rising air, its temperature will always be, if the wet adiabatic rate is so this is when the environmental lapse rate is less than the wet adiabatic rate, as the air rises, it will end up being cooler than the environment. So here, as air rises, the dry rate is 10 degrees Celsius per 1,000 meters. The rising air is 5 degrees, ends up 5 degrees. You have to start at 20. This would be 5 degrees cooler, 10 degrees cooler than the environment. The rising air is cooling faster than the surroundings, so it always wants to go down. Here, even when it's wet rate is 6 degrees Celsius per 1,000 meters, it's cooling faster than the environment. So the environmental lapse rate is about 5 degrees Celsius per 1,000 meters. If the wet rate is in this case, and then the wet rate is 6 Celsius per 1,000 meters. So it will all rising air will always end up, as you see here, the rising air is always colder than the environment at any elevation. These graphs are kind of confusing, but if they start at the same thing, it's always colder than the environment. And that is stable air. And the most important thing is that if this started warmer, because it's going down faster than the environment is, it will eventually catch up with the environment and stop, basically. So, this is a video about atmospheric stability. So, absolute stability is when the environmental lapse rate is less than the wet adiabatic rate. Absolute instability is when the environmental lapse rate is more than the dry adiabatic rate. And then there's conditional stability, which is when it's in between the dry and the wet adiabatic rate.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at atmospheric stability. And by the end of the video, you will have a better sense of what conditions cause the atmosphere to be stable or unstable. Okay, let's first consider this situation here. Look over at the left side of this picture and you'll notice that it's showing the environmental lapse rate there. In other words, that's how much the temperature changes with increasing altitude in the atmosphere. So it's around 25 degrees Celsius on the ground. It's 20 degrees Celsius, 5 degrees cooler at a kilometer of elevation. And then at 2 kilometers above ground level, you can see that it's dropped another 5 degrees to 15 degrees Celsius. Every 1,000 meters of elevation, we change our temperature by 5 degrees Celsius. Great. But doesn't that imply that those warm temperatures near the ground are going to want to rise up through those overlying layers? Well, it's actually more complicated than that. So that's what the right side of the picture is showing. This is adiabatic cooling. Now you remember that's basically where the air parcel ends up changing its volume, and that volume increase results in a lowering of temperature. In the example over on the right, we've got this 25-degree parcel of air. It rises up to a kilometer of elevation, and you can see that it expands and it cools to 15 degrees Celsius. So 15 degrees Celsius is less than 20 degrees Celsius. So it's actually more dense than the surrounding air. If you were to shove that parcel of air up to 2 kilometers in elevation, the same thing would be true. All right, it would expand even further, it would cool even further. Now it's 5 degrees in its temperature, and that is 10 degrees cooler than the surrounding air, which is at 15 degrees. So the overall tendency, this arrow over on the far right, the overall tendency is for that air to want to sink back down towards the ground. So in other words, we would describe this air as being stable. Absolute stability is the condition that we get when our environmental lapse rate is greater than our adiabatic cooling rate. So there's a dry adiabatic cooling rate, which is where the air is unsaturated and you don't have clouds. And then there's a wet adiabatic cooling rate where the air is saturated and you do have clouds. But so long as those adiabatic rates are less than the environmental lapse rate, you have absolute stability. So the air here is going to have a tendency to stay down close to the ground. And the only way you're going to get it to rise is if you bring in some air mass that wedges it upwards. So for instance, you get a cold air mass moving in and you get some frontal wedging and you drive that warm air aloft. So that's absolute stability. On the other end of the spectrum is absolute instability. This is the situation that we get when our environmental lapse rate is less than our adiabatic cooling rate. So our adiabatic cooling rate is greater here, whether it's dry or wet, whether it's unsaturated or saturated. And as a result, basically, as that air lifts off the ground, the difference in its temperature relative to the surrounding air ends up getting greater and greater. So basically, this sort of feeds back on itself, and that mass of air is just going to want to keep lifting up further and further and further away from the ground. So that's unstable. Okay, now the more interesting situation is this one. This is what we get when we have conditional instability. We have a stable air mass when it's unsaturated. In other words, when it's cooling at the dry adiabatic rate. But the wet adiabatic rate is greater. Once it crosses that critical condensation level, then we're going to be using the wet adiabatic rate, and so that is going to be greater than the environmental lapse rate. That is unstable once you reach this situation where the air mass is saturated. So we start off over here on the lower left where we have the rising air being forced aloft, but you can see that it's cooler than the surrounding air, so its tendency is to sink. But once it gets above that condensation level, you can see that its temperature is greater than the surrounding air, and so its tendency is going to be to rise. So when you get frontal wedging, a cold air mass moving in, and when that rising air gets shoved up above that critical level, then basically it takes over and it keeps on rising due to its own ever-increasing buoyancy relative to the surrounding air. So that's stable at one point, but then it rapidly converts to being unstable once you get it above that critical elevation. Thanks very much for your attention. This has been another Smart Figure.
So, absolute stability, if you push a packet of air up, it'll want to come back down. Absolute instability acts like hot air balloon. If you push a packet of air up, it ends up warmer than its surroundings and less dense than the surrounding air. So it will continue to rise until it reaches an altitude with the same temperature. This happens when the environmental lapse rate is greater than the dry adiabatic rate. So that shoots up. So this is absolute instability. You can see the rising air over here is always warmer than the surroundings. And I did not want to do that. So, come on. No. Oh, now it's black. The way just evolved. Oh. Nope, nope, nope. This card. No, I did. Just no. Sometimes I really hate the smart board. Because it is not smart. Mainly because there's no easy way to just turn it off. Conditional stability occurs when the atmosphere is stable for an unsaturated particle of air, but unstable for a saturated particle. So things are stable until you hit the dew point, and then they rocket upwards. And stability determines to a large degree, the kind of clouds that develop and the intensity of the precipitation. There's also some other strange things. You can get like a thermal inversion, where you get warm air above cold air. That can have some interesting effects. But yeah, that's the general idea. So this is conditional instability. So here you'll see it starts rising up. It's below, the temperature of the air is below the purple line in the environment. Then it starts condensing and it gets steeper. And there's a point here where it transitions and it stops dropping down and it starts shooting up. And then I'm pretty sure that's how you get those nice big thunderheads. So when air is removed below its dew point, the water vapor in the air will change into a liquid. It will become things like dew, fog, or clouds. Now, turn into a liquid, water vapor requires a surface to condense on. So it needs to have a surface that it can condense on to become a liquid. Now, for dew, that's just whatever surface is around. But in the air, it uses things like dust, smoke, ocean salt crystals work great because they're water loving, they're hygroscopic. Any little particles that are in the air, pollen. This actually helps clean pollutants out of the air because they get sucked into water droplets that fall as rain. Now, clouds are made of millions and millions of minute water droplets or tiny crystals of ice, depending on the temperature. So around here, a lot of the higher up clouds, ice. So just in general, as you go up, it's going to change from being droplets of water to ice. And we live far enough north that usually most of the clouds we see are tiny crystals of ice. And clouds are classified based on two things: their form, their shape, and their altitude. So what they look like and how high up they are. There's three basic forms. There are cirrus clouds, which are these wispy, thin clouds that the name has something to do with like kind of like eyelash, or I don't remember exactly where it comes from, but they look, very thin, wispy clouds that almost only occur very high up. They're white, they're thin. Your cumulus clouds, these are globular cloud masses. They're often associated with fair weather. A cumulus cloud is your classic little fluffy cloud. Yeah, the cloud you think of when you draw a cloud. It's the lumpy one. It means heap. So the one that's piled up like a heap. And then stratus, the sheet or layer of cloud that covers most of the sky. So the flat sheets of cloud that cover most of the sky on like an overcast day. That is a stratus cloud. And then there's also the altitude, the height. There are high clouds. High clouds all have cirrus in their name because cirrus clouds only occur very high up. The process that makes those thin, wispy clouds only occurs at very high altitudes, above 6,000 meters. So you have cirrus clouds, cirrostratus clouds, which are stratus clouds very high up, and cirrocumulus clouds, which are little lumpy clouds very high up. All the high clouds are very sort of thin. Then there are middle clouds. The middle clouds have alto in their name because alto means middle. You may have heard of an alto soprano. That's a middle soprano. That's what middle means. These are the alto stratus and alto cumulus. And that's between 2,000 to 6,000 meters in altitude. And then there are low clouds. These are below 2,000 meters. These include stratus, stratocumulus, and nimbostratus. Nimbo means rain. So if a cloud has nimbo in it, it's one of those dark clouds that's threatening to rain on you. That's a nimbus cloud. That just means raining. And then there are a couple clouds that fall in outside of the normal height categories. These are clouds of vertical development. These are ones that are spread out. They're so tall they cross through the areas. These go from low to high altitudes. These are called cumulonimbus clouds, or more colloquially, thunderheads. These often produce rain showers and thunderstorms. So here's a chart showing the different sorts of clouds. Cumulus cloud is sort of down near the surface. Stratocumulus is sort of a mixture of stratus and cumulus. They're like broken up stratus, but lots of them. Stratus is a low sheet. Nimbostratus is a rainy sheet. Altostratus and altocumulus are at the middle heights. Cirrostratus and cirrocumulus are all high. You notice they're all kind of thin. And then a cumulonimbus is the enormous thunderhead. There's a few other types of clouds that don't quite fall in these categories, but they're not going to come up on any of the tests. You could have like lenticular clouds or that can occur above like mountaintops where clouds are being formed by air being pushed up by the geography and things like that. So this is about types of clouds.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the different types of clouds. And by the end of the video, you should be able to use two different characteristics of clouds, their shape and their height in the atmosphere, to assign a name to them. Okay, so here's the figure from your textbook that discusses cloud types. You'll notice that it's organized according to layers in the atmosphere. So we're going to discuss clouds that form at high levels in the atmosphere, over 6,000 meters or 6 kilometers, middle levels in the atmosphere between 2 and 6 kilometers, and then everything below 2,000 meters are considered low clouds. We're also going to look at the shape of the cloud. So we want to think about the cirrus shape, which is sort of a feathery or wispy appearance, sheets or layers called stratus, and then globular masses, which are called cumulus. Finally, we want to take a look at vertically developed cloud masses over here in the final column. So let's go ahead and take a look at these one by one. Let's begin in the upper left corner with high wispy shaped clouds. Those are called cirrus clouds. Generally, those are only going to be found up at really high levels in the atmosphere. Stratus is the shape. If we're still high in the atmosphere, we're going to call it cirrostratus. You notice that it's got some wispy aspects to it, and as the sun shines through it, it makes that sort of aura around the sun. Next up, moving over to the right, we've got cirrocumulus. Cirrocumulus are high globular clouds. We've got altostratus right here. Altostratus occur at middle altitudes, and you can see that they seem to have a layered appearance. And then at that same altitude, maybe you'll have the globular masses. That would be altocumulus. So alto is the prefix for both of those, and then their shape, stratus or cumulus. Down below, we've got nimbostratus. Those are rainy clouds that are down pretty close to the ground. Generally, they're a little bit higher up, though, than stratus clouds. So stratus clouds will be relatively thin, and they'll be closer to the ground. Stratocumulus are classic good weather clouds. You can see that they look puffy, like kind of cotton balls hanging out in the sky. Over here, if you've got larger masses, we might call them cumulus that aren't in layers. And then those cumulus can actually advance upward through the different layers of the atmosphere to make cumulonimbus clouds. And these are thunderheads. Oftentimes they have sort of an anvil shape at the top. You can see how it kind of overhangs up there at the top. That's typical of cumulonimbus clouds. And those are the real dangerous weather formers. Okay, let's quiz yourself now. Let's take a look at the images that we've got here. What sorts of clouds are we looking at? Let's take the left first. I'll give you a hint. These clouds are at medium levels in the atmosphere. And you can see that they're relatively sheet-like. So that would be altostratus. Okay, good. Over on the far right, you can see that towering sort of thunderhead kind of shape. So what is that? That's clearly going to be a cumulonimbus. That's probably the easiest one to spot. Over here on the left, what do we have? Pretty classic looking cumulus clouds there. They're not really in a sheet, so I wouldn't really call them stratocumulus. And then over on the right, let's take a look at that one. Sort of dark and relatively rainy looking clouds. So that's probably nimbostratus there. Okay, on the left, you can see feathery, wispy shapes. So that should instantly tell you that's got to be a cirrus cloud. On the right, looks pretty high up there, and you can see the little globular masses. So cirrocumulus. Good job. Final two here. Over on the left, you can see there's a high layer of little ice crystals through which the sun is shining, and it's making that classic looking ring around the sun there. So this would be a nice example of cirrostratus. Finally, over on the far right, we've got sort of a medium altitude layer of puffy looking clouds. These would be altocumulus. Okay, hopefully you got those. If you didn't, go back and take a look at the images again. There are photographs in your textbook that you can also use to review. Thanks a lot for your attention. This has been another Smart Figure.
Now, fog is just cloud at the surface. It's a cloud with its base at or near the ground. It's considered an atmospheric hazard. If you've ever had to drive on a foggy day, you understand why. And most fog bursts because of either radiation cooling or the movement of air over a cold surface. So something has to cool the air down to cause it to become a fog. So you can either have warmer, more humid air passing over a cold surface, cooling down, forming fog, or you can have radiation cooling. The cooling during the nighttime, air cools down, condenses into a fog. A radiation fog is caused by the fact that the Earth's surface cools rapidly. So during cool, clear, and calm nights, it's very easy for the Earth to radiate away its heat and drop in temperature. And then that will cause the air above it to cool, and it can drop it below the dew point and cause a fall.
Like lakes?
No, like land, solid land. Lakes, bodies of water cool more slowly. You're going to get more something like advection fog, where warm air moves over a cool surface on a lake. So the lake, if the lake is cooler than the surroundings, but water is hard to change the temperature of.
Yeah.
So this is where actually, if you have land, and then it's nighttime, there's no clouds, that land cools down very quickly. And so the air above it also drops in temperature, and you get a fog there. An advection fog is when warm, moist air moves over a cool surface. So this can happen over bodies of water. It's common in the winter. You can also get an upslope fog, where humid air moves up a slope. Adiabatic cooling forms and it turns into a cloud. But yeah, like over a lake, that would be an advection fog usually. Because you had warmer air with more water in it, goes over the cooler water, cools down. You see it over like the Bay in San Francisco as well.
Yeah.
So this is an advection fog. So the Bay is much cold water, and moist air comes off in, hits the cold water, forms a fog. So there are also evaporation fog. So if cool air moves over warm water and moisture gets added to the air from the warm water, then the water will have a steaming appearance. That's a steam fog, an evaporation fog. And then you can have a frontal fog or a precipitation fog. And this forms during frontal wedging, when warm air gets lifted over cooler air, and rain basically evaporates to form fog. So here's a map showing the places that have the average number of days per year with heavy fog. You can see where you have like a cold current coming in, cold air. You get lots of fog over here. So here you're getting advection fog. Here you're getting radiation fog where the the land is cooling off very quickly at night. Around here we get advection and radiation fogs. And then stuff moving in. So here's a short thing about the types of fog.
Hello, this is Callan Bentley. Welcome back for another Smart Figure video. This time we're going to take a look at fog. And after watching the video, you should be able to describe how the 5 principal types of fog form. So fog, if we need to define it here, and we probably do, is basically a cloud that's sitting on the ground. So there's really nothing fundamentally different between what we see in the sky as a cloud and what we drive through very cautiously, like in this picture, and consider fog. It's basically just suspended water droplets in the air. So there are several different kinds of fog we need to consider. The first is a radiation fog. This is a kind of fog shown here in California's San Joaquin Valley that forms on cool, clear, calm nights. And this is basically when the ground is radiating away heat pretty quickly. And as a result, the ground cools off a whole lot. And then that actually can cause the air that's very close to the ground to be cooled below its dew point. The water will condense out of the air and it'll form a fog. Another example of a fog is an advection fog. This is what you get when you have warm, moist air moving over a cool surface. So here at the Golden Gate in San Francisco, the ocean is quite cold, and so the air is warmer than the ocean. As it moves over it, it triggers cooling of that warm, moist air below the dew point, so condensation makes a fog. This is advection fog. Another example of a fog is an upslope fog. This is what happens when you have air that's basically being forced up and over some sort of topographic obstacle. If it goes high enough, it will expand and cool adiabatically, and that can lower it below its dew point. So once again, condensation will form a fog in that circumstance. Upslope fog. This is an example of a local phenomenon called a steam fog. What's going on here is that you have relatively warm water and the air is the cooler one. So this is kind of like the opposite of advection fog. What's happening here is that the warm water is giving off lots of water vapor. It's hitting that cool air and basically recondensing immediately. Lastly, we have to consider the frontal fog, also called the precipitation fog. This is what happens when you have frontal wedging, so a warm air mass meeting a cool air mass. The warm air mass is shoved up, that triggers rain, and that rain falls down through the cooler air mass. Near the dew point, enough rain will evaporate to produce fog. This result is a more or less continuous zone of condensed water droplets reaching from the ground up through the clouds. Here's a map showing the average number of foggy days per year in different portions of the United States and Canada. You'll notice that there are heavy fogs, in particular along the coastal regions, so the Pacific coast, and then also in New England. There are cold currents in both of those places. We end up seeing advection and radiation fog along the Gulf Coast, and then upslope fog is particularly common, basically where the Great Plains meet the Rockies. Okay, let's test ourselves here. This is coastal Maine. We've got cold water here, and now you need to identify what kind of fog this is. Well, it's probably going to be an advection fog because Maine is right there adjacent to one of those nice cold currents. So those cold currents basically can interact with warm air above them and trigger advection fogs. Thanks a lot for your attention. This has been another Smart Figure.
Okay, so now we have a little time. So let's talk about how precipitation forms in clouds. When clouds form, there are a bunch of tiny droplets. They're less than 20 micrometers in diameter. They fall incredibly slowly, and they can be easily lifted back up by various factors. So something needs to occur to cause those droplets to get bigger, for them to fall out of the sky and onto your head. And there's two main ways that this can happen, depending on the temperature, basically. The more common process that occurs around here and more northern latitudes when it's colder is the Bergeron process. So this is the way that pretty much all the rain you encounter is formed. in the cloud, the temperature is below freezing. And it turns out that ice crystals, ice will condense from water vapor more easily than liquid water will. So what will happen is that anytime a little bit of a water droplet evaporates, it's more likely to freeze onto an ice crystal than it is to go back onto a water droplet. So what you get is that if water vapor, like water droplets, mix with the ice crystals will grow and the water droplets will shrink. So if there's any sort of mixing between layers of the clouds, you get the water droplets from below come up, the water droplets shrink, the ice crystals grow, you get large snowflakes forming, and then they'll fall to the ground. They'll either fall as snow, if it's cold at the surface, or they'll melt on the way down, which is what happens most of the time. And then they'll fall as rain. So what happens is you have a mixture of ice crystals and cloud droplets. Water vapor molecules will evaporate from the cloud droplets and condense onto the ice crystals. There's a preference towards the ice. The ice grabs water more strongly than the liquid water, water vapor more strongly than the liquid water. So the snow crystals will get larger and the cloud droplets will shrink because the snow crystals basically cannibalize all the water from the cloud droplets. The other way is in warm clouds. It's called the collision coalescence process. These are warm clouds that have larger hygroscopic condensation nuclei that form larger droplets. These droplets then collide with each other and then with other droplets during their descent and merge until they get bigger. Eventually they'll reach a maximum stable size, break into pieces, continue to fall and collect more water on the way down. And this is common in the tropics and over warm marine environments where there's a lot of water, it's relatively warm, but it's not, the clouds aren't freezing because the Bergeron process, the more common process, requires it to be literally freezing. It needs to be cold. So here you have a droplet forms. As it falls down, it merges with other droplets. It gets bigger and bigger. Eventually it reaches about 4 millimeters. It gets a depression at the bottom. It flattens out. And then at about 5 millimeters, it will break apart because it turns out a 5 millimeter droplet just isn't stable. And it'll break out into several droplets, which will repeat the process. So, here we have a large droplet falling. It gets bigger and bigger. It gets wider and wider. And then at 5, it breaks up into several large droplets that do the same thing again. And as stuff falls, this occurs. This can also happen in the lower parts of a cloud that had the Bergeron process creating droplets in the upper parts. So you can have both processes occur. So those are the two main ways that precipitation is formed. And the forms of precipitation are, things determined by the size of the droplets. Rain droplets are at least 0.5 millimeter in diameter. Drizzle droplets have less than 0.5 millimeter in diameter. Mist droplets are just large enough to be found. Snow is ice crystals or aggregates of ice crystals. So snow is when, ice crystals are falling from the sky. Sleet is clear to translucent ice pellets. You get when warmer air overlies colder air. So this is rain that froze on the way down. Glaze is freezing rain. So this happens when rain on the way down, it cools down and it gets cold enough that it should freeze, but it hasn't quite frozen yet because it didn't quite have the right conditions. And thus, when it hits a solid, it freezes. If you've ever seen that trick where someone pulls out a water bottle from the freezer and then slams it and it suddenly freezes. That's the same effect. It's super cooled water. It's possible to cool water below its freezing point without it starting to freeze, because for the ice crystals to form, they need something to format. So you can get raindrops that's super cool, and then when they hit something like your car, they immediately freeze, because the impact of the solid causes them to freeze. And that forms that freezing rain that just covers everything in a thin, awful layer of ice. So you start generally in the winter, you start with snow, but if the air below it is warmer, it'll melt and form raindrops. If you have a layer of cold air and then some warm air above it, it melts to form raindrops. And if that freezing layer is shallow, it super cools and becomes freezing rain. If the freezing layer is deep, it super cools and then enough happens that it actually freezes and becomes little ice pellets or sleet. And then if it's cold all the way down, you just get snow. It never melts. Ah. So those are the cold forms of precipitation. And then the most dramatic form of precipitation is probably hail. Hail are hard, round pellets that form in certain types of storms. These are pellets of ice formed up in layers with concentric shells. They most range in diameter from 1 to 5 millimeters, so they can get, the biggest hailstones are like the size of a baseball. And this occurs in cumulonimbus clouds that have big convection currents in them. So these things drop down and rise up repeatedly. So layers of freezing rain are caught in up and down drafts in the cloud. And basically each cycle, another layer is deposited on these hail pellets. And then the pellets fall to the ground when they become too heavy, which is why hail usually happens on a not so cold day. Because it needs those convection currents. It needs to get warmer and colder repeatedly to build up layers. If it's cold all the way down, it just comes down as snow. So hailstones, you have cycling repeatedly, and then stuff comes down as hail. So here's a big hailstone. You can see the internal layers. Because each time it cycles, it gets bigger. Rime forms on cold surfaces from the freezing of supercooled fog or cloud droplets. And we'll stop there for today. Have a nice day. We'll see you guys on Tuesday.